Hey everyone, and welcome back to PrepFusion. So this is the continuation of the conceptual question series. So previously we have been doing few questions. So one of the question was very interesting, that we had a non-unity feedback and we had to find a steady state error for that. So obviously this is covered in my full course, but according to the schedule it will come out later. So I wanted to share a part of that how we find the steady state error for a non-unity feedback system, as this is not taught anywhere in the YouTube, as I found. And this is a very interesting question, and if question comes up in gate, then there will be a lot of chances that there will be controversy. So this is from the full course itself. So I will just start the video after this, and we'll also solve one question. So yeah, let's start. Here we'll study about the steady state error for non-unity feedback systems. We'll understand the actual meaning of steady state error in non-unity feedback systems. Now, first I have drawn this block diagram, right? For a non-unity feedback system, this h of s is not equals to 0. H of s is not equals to 1. For a non-unity feedback system, our h of s is not equals to 1. That is what non-unity feedback system means. So I have broken down, like in the start of this time domain response also I have explained, or I think in the first basics chapters I've explained what is basically this whole block diagram, what is happening inside this whole block diagram. So there are many components, but I'm just taking 3 components here. So what are these 3 components? For a non-unity feedback system, like there is a controller which is controlling this processor and plant. This plant is giving some output, and we are sensing the output, and then again we're feeding it back to the system so that we can measure the error and minimize the error so that I can reach my steady state. So this is basically what is happening. Okay, I will explain each of these blocks in the next slide. What are each of these blocks? So this is basically a block diagram of control system with feedback. So I have just taken one example here. It may so happen you can take different examples also. Okay, I've just taken one example. What example did I take? Here I'm taking my processor or plant as a motor. So what does motor give me as output? Motor gives the rotation. Motor gives rotation, like fan is rotating or anything is rotating. Everything has a motor inside, whichever is rotating. So I'm taking my processor or plant as a motor. So if it is a motor, so we are taking motor that rotates at 2000 rpm when rated input is given. All this I'm assuming because I need to teach you something. That's why. Now what is the range of my motor? Range of my motor is from 0 volts to 20 volts. I'm giving like the motor safety range, working range is 0 volts 20 volts. If I give it 0 volts, then the motor obviously will not rotate, and if I give it 20 volts, the rated voltage, it will rotate at the speed of 2000 rpm. Now this is about the motor. Now let's understand about the controller. So controller gives controlled input to the motor according to the sensor output and reference input. So here I have a reference input and sensor output. So according to these two, the controller will give some output which is the input to the processor. Now obviously this controller, what is this controller for? This controller is controlling this motor so that I can get my desired output, whatever output I want for this particular reference input. That is what the task of this controller is. So obviously it is programmed or something like that. So this is what my controller does. Now what are the working range of controller? The working range of controller is minus 10 volts to 10 volts. So this is plus 10 volts, minus 10 volts to plus 10 volts, minus 10 volts to plus 10 volts. This is the working input range of controller. You can give it minus 10 to plus 10. And what output I can get? I can get output as 0 volts to 20 volts. Now just assume that this is a linear scale. This is a linear scale. So this motor is also linear scale. Like if I am giving it 0 volts, I am getting 0 rpm. If I am giving it 20 volts, I am getting 2000 rpm. Now let's say I am giving it 1 volts. What output I'll get? You do it according to linear scale, then what it will be? It will simply 100 rpm. So just convert this into unitary method. Simply aptitude you use, and you will get 100 rpm. You give 10 volts, you will get 1000 rpm, like that. Here if my input is minus 10 volts, controller input is minus 10 volts, then the output that I am getting is 0 volts. Controller will give 0 volt signal. If I am giving it 0 volt inside the controller output isn't 0 volts, it is 10 volts. So do keep that in mind. The controller output isn't 0 when my input is 0 volts to the controller. So this is one thing. Now what is my sensor? Sensor basically senses the speed of rotation of motor and gives some voltage output accordingly. So let's take it for example, let's take tachometer. Tachometer basically directly it shows you the speed. So tachometer can be a sensor, and we are converting it into a voltage signal. Inside the tachometer, obviously it is converting that speed into voltage signal. So this is one example of sensor. So now what are the inputs for the tachometer? What is the working range? The input for the tachometer is 0 rpm to 2000 rpm. So if my motor rotates 0 rpm, like it doesn't rotate at all, so tachometer will give some signal output as 0 volts. Now if my input is rotating at 2000 rpm, then my tachometer signal will give 20 volts output, 20 volt signal. So these are the working range of this processor, controller and the sensor. All these three things and the outputs, rated outputs and the linear outputs basically. Now what is my reference input here? So I am assuming I am giving a reference input. Reference input is this signal, assuming I am giving it 10 volts. All these things I have taken it down to teach you explain you a very good concept. So all these numbers are taken down to explain easily like the concept of steady state error. So this I am obviously all this I am assuming. Okay. So now what I will do, I will explain you what is actually happening when I start the system. Now here I will just copy this block diagram. Okay. I'll just copy this block diagram. Now I will assume that everything here is ideal. What do you mean by ideal? Everything is working as I explained. Right? If the controller input is minus 10 volt, it will give 0 volts. If the controller input is 0 volts, it will give me 10 volts. As expected, everything is working ideally. There is no error at all. Everything is working ideally. So when the first case is ideal case. So everything is working ideally. So what I will do, what happened initially, I am giving it some 10 volt input signal. So if I am giving it some 10 volt input signal, initially I am assuming nothing is rotating, my motor is off initially. So I just started my motor, I just gave it 10 volts in the here. Then what will happen? Here my motor isn't rotating, so obviously the input to this sensor is 0 rpm. If the input to this sensor is 0 rpm, what will be the output? This is 0 rpm initially. So this is 0 rpm. Now the output will also be 0 volts. So this is 0 volts. So let me draw this with different colors. This is 0 volts. Now if this is 0 volts, then what is the amount of signal here? This is 10 volts. So here this is just a basic subtractor, nothing else. So this is 10 volts. So initially the controller input is 10. Now if the controller input is 10, what is my output supposed to be? Here we can see that if my controller input is plus 10, then my output will be 20 volts. So input to the motor is 20 volts. Input to the motor is 20 volts. Now if the input to the motor is 20 volts, now my motor will obviously try to go to what? Will obviously try to go to 2000 rpm. But will it go instantly 2000 rpm? Instantly? It can't, right? Because the motor has some inertia with it. It has some friction with it. It can't go instantly to 2000 rpm. Obviously, when you turn on the fan, right? Does it go instantly to the highest speed if you make the regulator at knob 5? No, right? It doesn't. Obviously it takes some time to reach to the highest speed. So obviously this motor will obviously try to reach 2000 rpm but will not reach 2000 rpm instantly. So this will try to reach 2000 rpm but will not reach 2000 rpm instantly. So let's say it reached 100 rpm. So if it reached 100 rpm, what will happen? Now this sensor again will convert this 100 rpm into a voltage signal. So what does 100 rpm represent here? 100 rpm, represent here as 1 volts. So my sensor will go to from 0 to 1 volts, the output of the sensor. Now this is 1 volts. Then what will be this signal input to the controller? Input to the controller, reference input isn't changing, so the input to the controller will be what? 9 volts this time. Input to the controller will be 9 volts. Now if the input to the controller is 9 volts, what will be the output? Output will be 18. Linear scale, right? Linear scale. So the input to the motor will this time be 18. The input to the motor is 18. So like the processor is 18. Now if the input to the processor is 18, what will happen? The motor basically. So this is motor, sorry. I'll just change it to motor. So this is 18 and this is the input to the motor. So this is the input to the motor 18. So now instead of trying to reach 2000 rpm, now it will try to reach what? 1800 rpm. So what happened? It was going more fast because it wanted to reach 2000 rpm and the difference was 2000. Now what happened? It has already 100 rpm speed and it is trying to reach 1800 rpm. So it will slow down a bit. Obviously the acceleration will be slower, if you understand. Now obviously it reached to, let's say, 200 rpm like this. Then again this sensor will sense this one. Again here the signal will increase, the difference will decrease, the control input will decrease, and this output will also decrease, and slowly this will keep on happening. This will keep on happening, and it must happen depending upon the type of the system. We have already studied, right? If the system is underdamped, then what will happen? If the system is underdamped, then the output will go a bit higher than the steady state output, and then it will reach steady state like this. So here if you observe correctly, when will my output reach steady state? The output will reach steady state when the input to this controller is 0. When the input to this controller is 0, then this will give constant output, and that will be my steady state output. So when the input to this controller is 0, what output am I getting? I am getting 10 minus 0, 10. So if input is 10, then output will be what? Output will be, so here is 0, right? Input is 0, 10 minus it is 0, so output will be what? 10. And if output is 10, motor input is 10, then what is my output? 1000 rpm. So steady state output is 1000 rpm. But what will happen? I'm assuming my system is underdamped. If my system is underdamped, then what will happen? Just for a slight second, it may go to speed 1050. That may happen, right? Now if this goes to 1050 rpm, then what will the sensor output give? The sensor output will give 10.5 according to this, right? 10.5. So here my sensor output is 10.5. Now if my output sensor output is 10.5 and this is reference input is 10, so here this becomes negative. Now control input is minus 0.5. Now if control input is minus 0.5, what will it give as the output? If it is minus 0.5, it will basically give what? 9.5. Now if the motor input is 9.5, then what will the motor will try to reach? The motor will try to reach to 950. So it will try to reach 950. Obviously it won't get there and it will oscillate, and at steady state it will reach 1000 rpm. Now this is the ideal case where everything is working ideally. Okay, as planned, everything is working ideally. So one thing I want to write here is that my output will reach steady state when controller input is 0. Very important. Output will reach steady state when control input is 0. Then only my output will reach steady state. And let's say if my system was critical damped, what would happen? Obviously it will never go to 1050. It will directly go to 1000 rpm and then stop. It will not show this type of response. So what is my steady state output? Steady state output equals to 1000 rpm in ideal case. In ideal case, and this is known as my reference output. This is known as my reference output. Now, what how the graph will look? I'll just draw the graph in brief for a overdamped system. This is for a overdamped system. This is T, and let's say this name as Y reference in the ideal case. In the ideal case, so Y reference this for underdamped case. If I talked about overdamped, this for underdamped case. I meant for underdamped case. Obviously, there will be some peak, and this will then settle to what? 1000 rpm. Now this will settle to 1000 rpm. Now if let's say this was critical damp, this will directly go to 1000 rpm. There won't be any oscillations. Zeta will be 1 here. So this is about my reference output. So I got my reference output from this case 1 when my system was ideal. Case 1. Now let's do it for case 2 when my system is non-ideal. What do you mean by non-ideal? I will explain. So case 2. Non-ideal. Now if I take the non-ideal case, just let me copy the block diagram. If I can, where is the, okay, here is the block diagram. This is the motor. Okay, so now what will happen? Again, my system is non-ideal this time. What do I mean by non-ideality? By non-ideality, I mean that whatever ranges I was giving you, right? For 0 rpm, this will give 0 volts. For 2000 rpm, this will give 20 volts. It may so happen there may be some non-linearity in the system, or there may be some non-ideality, like due to the outside and anything, right? Due to the atmosphere, anything, any non-ideality there may be due to friction, anything. So due to non-idealities, if I give it 0 rpm, let's say I'm not getting 0 volts, I'm getting some voltage, 0.1 voltage, then what will happen to the system? If I'm getting 0.1 voltage, then that will change the system parameters, right? That will change the system parameters. So that is what basically I'm explaining here. So let's say if my motor input is 10 volts, it is not giving me 1000 rpm, it is giving me 990 rpm. That may happen, right? Motor has non-idealities, motor has losses. The electrical people will relate. Motor has copper losses, motor has coal losses. So, and what happens? Like just bought the system today, okay, and 1 year after I'm using the system. So 1 year after, if I use the system, there may be dust in the system. There may be many things in the system, due to which this will not give me proper output for some input. That may happen, or this is not able to sense the proper input. That may also happen. So these things, due to these things, the non-idealities may come. Now let's understand what will happen here. So I am giving it reference input of 10 volts, a reference input of 10 volts. Now if I am giving reference input of 10 volts, initially what was there? Initial output was 0. So sensor again, right? This is giving me 0, this is giving me 10, and this controller will give some output. Let's say so input is 10, so this will give me 0 output. No, sorry, this is this is 10, so this will give me 20. What was the maximum controller output here, right? Yeah, this will give me 20. Yeah, this will give me 20. So if this gives me 20, the motor again will try to go 2000 rpm. But what is happening, let's say like it has reached steady state. What is the condition for steady state? The condition for steady state that the input to the controller should be 0. Now it may so happen that input to the controller isn't 0. Input to the controller isn't 0. It can be 0, it cannot be 0. Why? I'm explaining. Let's say what is happening is that when this controller output is 10 volts, this motor input is 10 volts, but this motor, due to some non-idealities, only rotating at 990 rpm. So like it has reached steady state, like the oscillatory nature that, as I told, it has reached steady state and it has reached 990 rpm when the controller output is 10. So what will this sensor convert? This sensor is okay. It may so happen the non-idealities may come in anywhere. I don't know where is the non-ideality. It is inside a box. I don't know where is the non-ideality. It may come anywhere. Okay, I'm just explaining you with one of the example. Now this sensor has output as 9.9, and what is the output here? It is 10.1. So input to the controller is 0.1, and due to some non-ideality, this controller is also not perfect. So this is giving me 10 volt. Due to some non-ideality, this is giving me 10 volt, and due to that, this motor input is getting 10 volt, and this is giving me 990 rpm instead of 1000 rpm. This motor has also some error in it due to some non-ideality. So I'm getting 990 rpm, and this is stop. This is reached steady state, and this has stop. Okay, I hope you understand. Due to friction, whatever. So what is this 990 called? This has reached steady state. What is this 990 called? This 990 is called the actual output. Actually, practically, which system I am currently using, the actual output that I am getting. And what was this output? This output was the reference output in case of idle system. So 1 year before, I used to get this output 1000 rpm in an idle system 1 year before. Now 1 year after, when I run the machine, when I run the control system, I am getting 990 rpm. Okay, so actually I'm getting 990 rpm, but what should I should have got? I should have got 1000 rpm. So this is basically the steady state error. So what is a steady state error here? Steady state error is 10 rpm, because actually I should have gotten 1000 rpm, but I am getting only 990 rpm. So steady state error is 10 rpm. I'll write the definition in the next few slides here. So let us compare the two with a graph basically. So basically the graph, if I'm assuming both systems are underdamped. So if both systems are underdamped, this is t, this is y of t. Now y of t is 2 here. One is the idle case. Idle case is like this one. This is 1000 rpm. And this is basically actual output. I'm drawing it with exaggeration, obviously, that this won't be that this much down, but to explain you and see clearly the difference, I'm drawing it. This is not to scale. This is 990 rpm. So this is 990 rpm. Now we are observing that this is my ideal output, like this is my reference output, and this is my actual output. So I'm observing there is a 10 rpm difference. So this is what this is my steady state error basically. So system, like here I've explained that system will reach steady state when my controller output is constant. So if my controller output is constant, it won't change. Then obviously this motor won't change, right? Motor won't change. Motor won't change its speed. So this is what I have written here. These are the key points that you need to keep in mind. But don't worry, I'm just explaining you the actual theory behind this. When you will solve the question, you just have to solve it using one thing that you need to keep in mind. For explaining the concept behind this, I'm explaining this, right? Now, as I explained, non-idealities may be present on the controller, motor, or sensor. Anywhere it may be present. So this is about the non-ideal case and the ideal case. And I have also explained about the steady state error. Now let's go to the definition. So in case of non-unity feedback, the actuating signal, error signal may or may not give steady state error. So yeah, this is about the unity feedback. Unity feedback we used to tell, right? The actuating error signal is the steady state error, because where was the actuating error signal? Actuating error signal was here. Actuating error signal was here, if you remember correctly. So it may not give the steady state error depending on the form and purpose of the feedback system. I will explain this later. So what will give me error? What will give me steady state error? Steady state error will give me reference output minus actual output. So what is reference output? The reference output is the output that we get when my system is ideal. System is idle. There are no error. There are no non-idleness in the system, in the controller, in the processor, in the sensor. And what is my actual output? My actual output is the output of the system due to non-idleness, due to non-idleness with the same reference input. I should write here with the same, not due to, with the same reference input. No, with the reference input. With the same reference input. So this is what my actual output and reference output is. Now this is my error signal. So let's go for the derivation. How will we write the error signal in Laplace domain? That is the important point, right? To write the error signal in Laplace domain, that's how we'll solve the questions. And only once this has come in gate examination, so don't stress too much. And also when it has come, they haven't used this concept, they have used some other concept, that also I will explain. Now this is my block diagram. Like, this was my actuating signal basically, and this was my actuating error, but we're not interested in actuating error. We're interested in the steady error signal. Now what is error signal? So how you will use the procedure? How will you proceed basically when you have non-unity feedback and you need to find error? What you will do? First, you will assume ideal case, and if you assume ideal case, you want this controller input to be 0. You want this controller input to be 0, then only my output will reach what? Reference output. Then only this controller input, then only this controller input will be 0, right? It has reached reference output. That means it has reached steady state. So if it has reached steady state, here the input will be 0. If the input here is 0, then this C reference of S into H of S, which is in minus sign, plus R of S, will be equal to 0. This is what this is saying, right? Controller input should be 0. So what we'll do? Case 1. Ideal case. Ideal case, obviously my y of t will reach y reference when the controller input is controller is 0. Control input is 0. So control input is 0, then it will reach reference. Now what is happening? How it will reach 0? Obviously this R of S minus C of S into H of S. C of S is C reference of S. C reference of S into equals to 0. So this is what my like equation will be, right? This controller input should be 0. So from here we can find our C reference of S. So what is my C reference of S? C reference of S is R of S by H of S. This is my C reference of S. Now we'll go to case 2 now. Now we are interested in the actual output. Actually what output I am getting when my system is not ideal, when my system is practical. So when my system is practical, what will happen? My actual output will be simply C of S, C of actual of S will be what? Simply that formula, right? What is the formula? R of s into T of s. Simple transfer function. Simply this is the like the whatever the input is and multiply the transfer function is my C of s. Simple thing. Or G upon 1 plus Gs equals T of s. That also you can write. So what I will write here? What will be my error signal? My error signal will be R of s by H of s. First I should write this like this, that my error signal will be C reference of s minus C actual of s. So what is my C reference of s? It is R of s upon H of s. And what is C actual of s? C actual of s is R of s into T of s. So this is my C reference of s and C actual of s. Now this is basically my error signal. From here you can simply find your answer. So you don't need to remember anything. Don't need to remember anything. Okay. Either you can remember this formula or you don't have to remember this formula. I won't recommend you remember this formula. What I recommend is remembering these two cases. What we are doing actually, we're making this actuating error 0 in the ideal case. Like this is the actuating error, right? This is the actuating error. So we're making this 0 in the ideal case. And then we're calculating for non-ideal case. What is the actual steady state output I am getting, not a steady state, what is the actual output I am getting, and through that I am calculating my error signal and what will be my steady state error. So my steady state error will be s limit s tending to 0 s. I can take R of s common here, right? First of all I will write T of s, right? I will explain T of s, else few people will get confused. T of s will be G of s by one plus G of s into H of s. Very important. This is T of s. You can expand this or you can keep it as it is. Doesn't matter. Now this is limit s tends to 0 s R of s into 1 by H of s into T of s. So this is what my steady state error will be. So yeah, you can put s equals 0 over here and you will get your answer, right? So I want to further deduce this. T of s you can write this like this. No need of that. When you will solve question, you will see. You will see. One more thing I want to tell it to you. Like I told, right, this signal was the actuating error. Now if in the question they have written this as E of s, and then they ask you find my steady state error, then what will you do? Will you use this one or will you just find this E of s and then do s E of s limit tends to 0? You'll do this one only. Okay, if in the exam they have given you E of s here and they want you to find the steady state error, then you will not use your brain. Just use what? Just use find this E of s. Okay, just let me write the E of s here. Find this E of s with the help of block diagram reduction technique or SFG, whatever is suitable, or the unknowns that I used to take. You take any of those, then what do? You just use the final value theorem, limit s tends to 0 s E of s. You just use that, nothing else. No need to use your brain, because the definition of error, steady state error, has been given differently in different books. So this is the best explanation that I found out for the steady state error for a non-unity feedback system. I'm talking about. For a unity it is very easy. For a non-unity feedback system, but generally like one time only GATE has given question on non-unity feedback system for steady state error, and that also time they have given this E of s. They have written down that E of s is this. They explained, right? This explained. So if they've explained, if they're giving it to you that E of s is this, they're defining it for you, then you don't need to define it by yourself. No need to use brain. Just simply use this final value theorem. Find this E of s with the help of any block diagram redirection technique or whatever, and then you use the final value theorem. So here, like they're telling me this is the my error steady state, like error signal will be actuating error signal. Okay, but in general they are different. I explained you why with the whole concept. But if they are telling you that you need to find this one, they're telling you to find this one, you will find this one. So this is the important point to note here. Now let's do a few questions, and from there our concept will get more clear. So first we have to find the steady state error expression. They have not asked to find the steady state error. They just want to find the steady state error expression. Why? Because they haven't given us any input. For any general input, we have to find the expression in Laplace domain of the following system. So system is given, and we have to find the steady state error expression. So first thing what I want to warn you is that you shouldn't use what? You shouldn't use this formula. Limit s tends to 0 s r of s 1 minus t of s. You shouldn't use formula. You shouldn't use this formula. Why? Because this is only valid for unity feedback systems. This is only valid for unity feedback systems. Like this can also be used here when what? When my this feedback factor h of 0, like feedback factor becomes 1 at steady state. Then also you can use. I will show you with one example. But for now, we can't use this in a non-unity feedback. So only used for unity feedback system. Now how will I calculate? As I mentioned, right, first I will calculate the ideal case, and I will calculate my reference output from that ideal case. So case 1, so my case 1 is ideal, then obviously my r of s minus this y, this is y, right, this is y reference of s into h of s should be equal to 0. I am not putting the value of h of s now, I will put it at the end. So y reference of s is, just hold on a second, let me check if it is recording or not. Yeah, everything is recording. Fine. So y reference of s is r of s by h of s. So this is what my y reference of h is. Now let's go for the second case. So what is the second case? Second case is the non-ideal case. Just non-ideal case. Non-ideal case. So what is happening in the non-ideal case? So in the non-ideal case, my y of s is simply y actual of s simply equals to r of s into t of s. I will write the t of s at the end. So what is t of s? T of s is simply g upon 1 plus g of s. So what will be my error signal? Error signal will be this y reference of s minus y actual of s. So it becomes r of s by h of s minus r of s into t of s. Now like you can take a common r of s, and this is 1 by h of s. You could have directly written this, like if you like want to remember this, you could directly written this, or don't have to, you can derive also. This is e of s. Okay, like in the unity feedback also you can simply derive, no need to remember the formula. What was the formula, like what was the derivation there? Simply it was the actuating error and the this simple error signal were same there, because it was unity feedback. So there, what I used to do was r of s minus c of s was equals to my error signal. Okay, simple actuating error signal was the error signal there. Don't need to remember anything. Now what you do, you put the value of h of s, you put the value of t of s. So if you put the value of like first, for steady state error, limit s tending to 0 s e of s. So this is equals to s e of s. So this is equals to s into r of s. So limit s tending to 0 s into r of s 1 by h of s. What is h of s? H of s is equals to this 6 into s plus 1 divided by s plus 2. 1 by, it was 1 by h of s, so this is 1 by, and this is plus t of s. So t of s I will write it separately because this will make this messy. T of s is g upon 1 plus g of s. What is g of s? G of s is 1 by s plus 3 divided by 6 into s plus 1 divided by s plus 2. This is a h of s, and h into g of s also we have to do. This is 1 plus s plus. So what will this become if I multiply s plus 3 into s plus 2? This will have s plus 2 here. This one will have s plus 2 into s plus 3 plus 6 into s plus 1. This one will become s square plus 5s plus 6 plus 6x plus 6 s plus 2 divided by s square plus 11s plus 12. Now this one will become this. Now what will happen? So if I just write it here, minus, what was this, minus t of s. So this will be s plus 2 divided by s square plus 11s plus 12, and this s plus 2 will go in the numerator, right? This s plus 2 will go in the numerator. So I'm just doing it here. You can do the rough calculation by yourself. This s plus 2 will go here. Like I'm just writing the expression, like the question is done itself, it doesn't matter. So this is just a theoretical question basically. So my es of s equals to limit as s tends to 0 s r of s. Simply I can take s plus 2 also common here. So if I took s plus 2 equals to common, I can put s equals to 0 for s plus 2. So this will become 2 itself, right? If I put s equals to 0, or I will not put, I will just take common here s plus 2. At the end I will put s equals to 0. Here this is 1 by 6 into 6s plus 1. Like this is 6 s plus 6 basically. Six s plus 6. Now what is this? This one is s square plus 11s plus 12. S square plus 11s plus 12. So like I'll just do cross multiplication, simple. So this one will be s square plus 11s plus 12 minus what, 6s plus 6, 6s plus 6, and we have in multiplication 6s plus 6 into s square plus 11s plus 12. So here if I just, now I can put s equal to 0 because I can't take common any s term common here in the numerator or denominator. So that's what I was waiting for. So any common term in the numerator denominator, that's why I solved it until here. Now I can put s equal to 0 over here. So this one can come outside. So if I put s equal to 0, this will go to 0, this one will go to 0, this one will be 12, this one will go to 0, this one will be 6. So this one is in minus. So 12 minus 6 is 6. This one will go to 0. So here I am remained with 6. This one will also go to 0. This will be 12. So 6 into 12. And here in the numerator I have 6. So 6 cancels. So I have 1 by 12. And this one, if I also put 0, so this one will go to 2. So if this one goes to 2, then this is 6 cancels. So 1 by 12 to 1 by 6. So basically my final expression will be 1 by 6 into limit s tending to 0 limit s r of s. So this is what my final expression will be. Now doing anything wrong here? No, this is correct only. This is correct only. This is correct only. Fine. Okay. So yeah, this is the expression. Okay, whatever depending on the input. Let's say if my input was a unit step, then it would be 1 over s. So this one would have been cancelled. Simply s equals to 0 we can put, and my steady state error will be 1 by 6. Depending on the input, whatever my input is, my steady state error will be defined like this. So this is my answer to this question. Now let's go to the next question. What is the next question? The next question is telling us to find the steady state error of the following system. So the system is given and we have to find the steady state error. Obviously we are observing that this is not a unity feedback system. So this is not a unity feedback system. Again, right, I will use the same thing. I can do copy paste, but you shouldn't. So what I will do, I will do the same thing, that I'll just copy this one. I'll consider case 1 as ideal case. So what will be my y reference of s? So my y reference of s will be simply r of s. Like input is given 3 ut, right? Input is given 3 ut, and this is my y reference of s. R of s by h of s. So what is h of s? H of s is 3 by s. You can either put at the end or you can put at the start. Doesn't matter. Okay. And what about my case 2, non-ideal case? Just copy this one. For non-ideal case, just hold on a second, let me drink a bit of water. Sorry about the interruption. Now if like y actually is this simple, y actually is always fixed, r of s into t of s. So y actually is this one. So now this is my error signal. This is what I can write, or I can take my r of s as common. One by h of s. H of s is what? 3 over s. So this will 1 by h of s will be s over 3 minus r of s. R of s is, like, I have taken r of s common. What is t of s? So let us find the t of s. So t of s will be g of s upon 1 plus g of s into h of s. What is it? So it is 1 by s plus 3. Write this here in small, like I don't have enough space. One plus 1 by s plus 3 into 3 over s. So I will multiply this s into s plus 3 on both numerator and denominator. This will be s divided by s square plus 3s, s into s plus 3 plus 3. So this is what my transfer function is. Now if this is my transfer function, here I can write s divided by s square plus 3s plus 3. Okay, I can take s common here. So if I take s common here, what do I get? I'm getting limit as s tending to 0. Like I have taken s common, s square r of s. So this is my steady state error. I haven't written it, sorry. This is my steady state error. Into 1 by 3 minus 1 by s square plus 3s plus 3. Limit as s tends to 0, s square into r of s. So this one becomes s square plus sorry, in the numerator I had 3, no, I didn't that. S square plus 3s plus 3 minus 3 divided by s square plus 3s plus 3. So this is what I get. So now this one will get cancelled. Okay, so this one gets cancelled. That's why 3s plus 3, and here I have a 3 also. So if this one gets cancelled, I am remaining with s square plus 3s. So I am remaining with s square plus 3s. So I can again take s common, s cube into r of s. This is s plus 3 divided by 3 into s square plus 3s plus 3. So now, like simply, what is my r of s? R of s is what? R of s is 3 u of t. So r of s is like r of t is 3 u of t. So r of s will be 3 by s. 3 by s. So even if you put 0 here, limit as s tends to 0, s cube into 3 by s, and this is simply s plus 3 divided by 3. This 3 gets cancelled, but it doesn't matter. Why? This one becomes 3s plus 3, and this one cancels out, but this s also gets cancelled. But what are we remained with? Simply this s goes to 0. So if this s goes to 0, so we are remained with 0 itself, right? 0 into, like this, if I make this s square 0. Now if this is what? 0 plus 3, 3. 3 by 3 is 1. So this is 0, this is 0, this is 3 into 1. So simply we are getting 0. So our steady state error is 0. This is my answer. If they haven't provided my any error signal, if they haven't provided with any error signal, so my steady state error will be 0. Now what can be the wrong approach of this one? So in few books I've seen in few books, they've given that what you can do, you can convert it into unity feedback system. So this is my wrong approach. What can be wrong approach? Wrong approach could be to convert this non-unity feedback system into unity feedback system. So how you will do? Simply, what you'll do, just let me first take the block diagram. You have the block diagram here. So you take the block diagram. Now you want to convert this into unity feedback. What you will do? You will make a new system, and in the new system what you will do is, just let me copy the same thing here, whatever this is. I just change the things. This function will change, g of s will change. This will be some g dash of s, and this will be 1. Like few books they have given this method, that what you can do, you can convert this into unity feedback. So this has converted into unity feedback. So now my transfer function will be same. Like that is the main motto, that obviously, like, I'm changing it to unity feedback, then the system will be changed. How can I make it same? How can I make my response? So they are talking about that response should be same. Obviously this is wrong approach, but still I'm telling you like what they are talking about. They're talking that my response should be same in both system in any given input, right? In any given input, the response will be same in both of the systems, system 1 and system 2. 1 and 2. Now one is unity feedback and another one is not unity feedback. Now how will the response be same? How is my response related? How is my c of s related? Or how is my y of s related? Is related with the transfer function. Y of s is equals to r of s into t of s. So for any given input is same. So what else need to be same for my c of s to be same? C1 of s and c2 of s. For c1 of s and c2 of s to be same, my transfer function should be same. That is what they're doing. They're equating the transfer function t of s equals to g dash of s upon 1 plus g of s. From here they're finding my g dash of s. Now what they're doing, they're using the simple steady state formula for unity feedback. So what was the steady state formula for unity feedback? Like you find the g dash of s from here. Okay, you find the g dash of s from here. I won't find it because we won't even need it. Anyways, they're wrong. So what they're doing is finding the unity, like steady state error, and what they're doing is limit s tends to 0 s e of s. Now what is s, like e of s? Limit s tends to 0 s into r of s minus c of s. If you remember, right, basically it was the actuating error signal itself. Or you can write here, we have taken y of s, so you can take y of s. It doesn't matter. Y of s. So now let's see what answer we get according to their method. So this is limit s tending to 0. Obviously I will take r of s in common, so r of s is in the outside. 1 minus y of s on r of s, which is equal to t of s. Now what is my t of s? T of s I have already derived it here. This is my t of s. So my t of s is s divided by s square plus 3s plus 3. So I will write the t of s directly here. So this is the this one, and if you simply subtract these, so I will, what is r of s? R of s is 3u of t, 3u of t here. R of s is 3, like I've written it down. This is 3u of t. R of s is 3, like not r of s. R of t is 3u of t. So r of s is 3 by s. 3 by s. This is s square. So s square plus 3s plus 3 minus s and this is 3. This one was 3 by s. Am I doing previous question? I did anything wrong here? Okay, this one was 3 by s, right? Yeah, s went over and s, yeah, that is fine. So this one will become s square plus 3s plus 3, right? So obviously here nothing is getting cancelled or something. This s is getting cancelled, and what am I getting? If I put s equals to 0, what am I getting? If I put s equals to 0 over here, this is not the end. If I put s equal to 0 over here, what do I get? So this one will be 3, and here this is 0 0, and this is 3 minus 0. So numerator I have 3, this is 0 0, and denominator also I have 3. So 3 by 3 is 1. It's 1, which is 3 itself. So is this correct? This is not correct. This is not correct. Obviously this is absolutely incorrect. This will never be correct, because you are changing the internal behavior of the system. There is some sensor here, there are many things here, right? You're just changing the internal behavior of the system. You're converting it to from a non-unity feedback to unity feedback, and then you're calculating the error. You will not get the same answer. Okay, only the output response will be same, because your transfer function is same. That is mathematically correct. Mathematically, yes, this is correct. Response will be same, but we are not talking about response here. We're talking about the error signal. So that will obviously be different here. So just be careful. We can't use this method. We won't be able to use this method. Another wrong approach will be to calculate the actuating error. Like you are calculating the error signal here itself. Okay, just few students assume that yeah, E of s is this, and you just calculate this now here, right? E of s is this, and they just calculate this y of s into h of s, r of s here. So r of s minus y of s into h of s, that is equals to E of s, and then you put s into E of s, limit s tends to 0, s into E of s, final value, and you will find your error. No, that is also incorrect. That is the actuating error signal. That is we are not interested in. But if in the question they have mentioned that this is E of s, then obviously, as I mentioned earlier, you will not use your brain. You will just simply find whatever you are doing it previously. You do the same thing here. You just simply do y of s into h of s, like r of s minus y of s into h of s equals to E of s, and then from there you find simple answer. So yeah, this was it for the steady state error for the non-unity feedback systems. In the next lecture we'll do few, yeah, sorry, actually the storage got full, so that's why we had to cut. So in the next lecture we'll do few assignment questions, and yeah, in that basically we'll wrap up. I think two more lectures and we may wrap up, and after that also we'll do a bit of summary of the time response. So yeah, thank you for watching. I will see you in the next lecture.